Hello everyone, you are welcome to the educational material prepared on engine fundamental, and which is the sixth part of the presentation document. The topic we are going to discuss is classification of internal combustion engine. The learning objective. After this presentation, the student shall be able to classify internal combustion engine and measure the engine size. The content. The student shall learn classification of internal combustion engine measurement, such as bore, stroke, displacement, and engine volume. The required material: practice car, diesel engine, diesel engine trainer, petrol engine trainer. Classification of internal combustion engine. Today's automotive engine can be classified in several ways depending on the following design features: the operational cycle, the number of cylinder arrangement, valve train type, ignition type, cooling system, fuel system, firing order, engine rotation, combustion, engine configurations, camshaft and valve location, and engine location. So by using these all different parameters, classification of engine can be take place. Let's discuss about the first classification, which is based on operational cycle. Most technicians will generally come in contact with only four-stroke engine. However, a few older cars have used, and some cars in the future will use a two-stroke engine. So based on the operational cycle, we have a two-stroke cycle engine and a four-stroke cycle engine. The two-stroke cycle engine completes the working cycle within the two-stroke and with one revolution of the crankshaft, while a four-stroke engine completes the four-stroke with two revolution of the crankshaft. The number of cylinder. The engine can be classified based on the number of cylinders. So the current engine design include 3 cylinder, 4 cylinder, 5 cylinder, 6 cylinder, 8 cylinder, 10 cylinder, and 12 cylinder engine. This picture shows the different type of inline engine based on the number of cylinder. The twin are 2 cylinder, 3 cylinder, 4 cylinder, inline 5, inline 6, inline 8. And this picture shows the type of V engine. V2 engine, V3 engine, V4 engine, V5 engine, V6 engine, V8 engine, V10 engine, V12 engine, V16 engine, V18 engine, V20 engine, and V24 engine. Cylinder arrangement. So based on the cylinder arrangement, we can also classify the engine. So the classification can be flats, opposed, or V-type. Other more complicated designs have also been used. This is V-type, and this is opposed, and this is the rotary, and this is the radial, and this one is L-line. Valve train type. Engine valve train can be either the overhead camshaft type or the camshaft in block overhead. Some engines separate camshafts for the intake and exhaust valve. These are based on the overhead cam design and are called double overhead camshaft engine. V-type double overhead camshaft engine have 4 camshafts, 2 on each side. The double overhead camshaft design is shown here. So the camshafts are 2 in number. So 2 camshafts operate the valve mechanism. And here it is the single overhead camshaft. So we have a single camshaft in the center, and this camshaft operates the intake and the exhaust valve. And this is the overhead valve. The valves are located inside of the cylinder, while the camshaft is located inside of the engine block. Ignition type. There are 2 types of ignition system: spark and compression. Gasoline engine use a spark ignition system. In a spark ignition system, the air-fuel mixture is ignited by an electrical spark. Diesel engine or compression ignition engine have no spark plug. A diesel engine relies on heat generated as air is compressed to ignite the air-fuel mixture for the power stroke. The cooling system. Based on the cooling system, we are classify engine into air-cooled and liquid-cooled. There is also engine which is oil-cooled. So there are both air-cooled and liquid-cooled engines in use. Nearly all of today's engines have liquid-cooled system. The fuel type. Several types of fuel currently used in automobile engine include gasoline, natural gas, methanol, diesel, and propane. The most commonly used is gasoline, although new fuels are being tested. So from this picture, you can see the different type of automobile fuel. The firing order is another parameter used to classify engine. An engine firing order states the sequence in which an engine's pistons are on their power stroke, and therefore the order in which the cylinder's spark plug fire. The firing order also indicates the position of all of the pistons in an engine when a cylinder is firing. For example, consider a 4-cylinder engine with a firing order of 1, 3, 4, 2. Cylinder order is 1, 2, 3, 4, but the firing order is 1, 3, 4, 2. These events are identified by what needs to happen in order for number 3 to be ready for next fire, and so on. Number 1 in compression, number 3 cylinder in intake stroke, and number 4 cylinder in exhaust stroke, and number 2 cylinder in power stroke. So number 1 compress, then power is produced in the next stroke. Then number 3 continue to the compression stroke and then continue to produce power. Common cylinder numbering and firing. For the engine configuration A line and V type, the number of cylinder 4. The firing order 1, 3, 4, 2 or 1, 2, 4, 3. The commonly used one is 1, 3, 4, 2. And for 6-cylinder inline engine, the firing order is 1, 5, 3, 6, 2, 4. For V-type 6-cylinder engine, we have different options for the firing order. The first firing order is 1, 4, 5, 2, 3, 6. Then the second is 1, 6, 5, 4, 3, 2. For the 8-cylinder engine, we have also similarly different firing order. 1, 5, 4, 8, 6, 3, 7, 2, and so on. Engine rotation. To meet the standard set by the FCA, nearly all engines rotate in a counterclockwise direction. This can be confusing because its apparent direction changes with what end of the engine you look at. So the direction is changed when you look at from this end and when you look at from the front. So this is the direction where the standard rotation of the engine can be observed. So in this direction, the engine is rotated in the counterclockwise direction. But if the observer is standing in front of the vehicle, then the engine is turning in the clockwise direction. So this is direction of rotation, and it is the standard one. So the standards are based on the rotation of the flywheel, which is at the rear of the engine, and there the engine rotates counterclockwise. Combustion. Combustion is the process in which the combustible substance burns in the cylinder to produce power. So the combustion can be normal or abnormal. For the combustion process, we need three separate things. The first thing is the flammable, and which is fuel, and we have a catalyst, which is oxygen. And to generate combustion process, we need heat or spark. So in the normal combustion, the rapidly expanding gas pushed down on the piston with a powerful but constant force, and complete combustion has occurred if the combustion process is normal. If the combustion process is abnormal, then when something prevents the complete combustion process, the engine will misfire or experience incomplete combustion. Misfire causes a variety of drivability problems, such as a lack of power, poor gas mileage, excessive exhaust emission, and a rough running engine. Engine configuration. Depending on the engine, either an inline, V-type, and a slant or opposed cylinder design can be used. The most popular designs are inline and V-type of engine. So we have also a W engine, a VR engine, and a radial engine. The radial engine is applicable in aircraft industry. Camshaft and valve location. The valve in a modern engine are placed in the cylinder head above top of the piston. The valve in many older engine designs were placed to the side of the piston. Camshafts are located inside the engine block or above the cylinder head. The placement of the camshaft further describes an engine. The overhead valve and overhead valve engine are mounted in the cylinder head and are operated by a camshaft located in the cylinder block. This is the overhead valve design. So the valves are located above the piston, and also above the camshaft. The other is the overhead cam. In the overhead cam, the cam is located above the valve. Overhead cam engine also has intake and exhaust valve located in the cylinder head, but as the name implies, the cam is located in the cylinder head. In an overhead cam engine, valves are operated directly by the camshaft or through cam followers or tappet. So in the overhead cam type of design, there is no push rods. Engine location. The engine is usually placed in one of three locations. In most vehicles, it is located at the front of the vehicle, in front of the passenger compartment. Front-mounted engine can be positioned either longitudinally or transversely with respect to the vehicle. The second engine location is a midpoint position between the passenger compartment and rear suspension. Mid-mount engines are normally transversely mounted. The third and least common engine location is the rear of the vehicle. Engine measurements: bore, stroke, displacement, engine volume, and also efficiency like engine efficiency, volumetric efficiency, thermal efficiency, mechanical efficiency. Bore and stroke. The bore of a cylinder is simply its diameter, measured in inch or millimeter. The stroke is the length between TDC and BDC. Bore and stroke determine the displacement of the cylinder. When the bore and stroke are of equal size, the engine is called a square engine. Engines that have a larger bore than a stroke are called oval square engines, and engines with a larger stroke than bore are referred to as being under square engine. Displacement. A cylinder displacement is the volume of the cylinder when the piston is at bottom dead center. An engine displacement is the sum of the displacement of each of engine cylinders. An engine with a larger displacement produces more torque than a smaller displacement engine. However, many of other factors influence an engine's power output. Engine displacement can be changed by changing the size of the bore and or stroke of an engine. Compression ratio is a comparison of a cylinder's volume when the piston is at bottom dead center to the cylinder volume when the piston is at top dead center. The compression ratio or CR is a statement how the air-fuel mixture is compressed during the compression stroke. Carbon and dirt buildup in the cylinder can change the CR. For example, if a great amount of carbon collects on the top of the piston and around the combustion chamber, the volume of the cylinder changes. This buildup of the carbon will cause the compression ratio to increase because the volume of TDC will be smaller. We can calculate the compression ratio by using the following equation. The compression ratio is equal to clearance plus swept volume divided by clearance volume. So the clearance volume is represented by Vc and the swept volume is represented by Vs. So Vc plus Vs over Vc, which is 1 plus Vs over Vc. Engine efficiency. Efficiency is simply a measure of the relationship between the amount of energy put into an engine and the amount of energy available from the engine. Other factors or efficiencies affect the overall efficiency of an engine. Volumetric efficiency. Volumetric efficiency describes the engine's ability to have its cylinder filled with air-fuel mixture. If the engine cylinders are able to be filled with air-fuel mixture during its intake stroke, the engine has a volumetric efficiency of 100%. Typically, engines have a volumetric efficiency of 80% to 100% if they are not equipped with a turbo or supercharger. Basically, an engine becomes more efficient as its volumetric efficiency is increase. We can calculate volumetric efficiency by using the following equation, which is volume of efficiency is equal to volume of charge at meters divided by swept volume. Actual airflow divided by theoretical airflow. So we can calculate it in either of the two equations. Thermal efficiency. Thermal efficiency is a measure of how much the heat formed during the combustion process is available as power from the engine. Typically, only 1/4 of the heat is used to power the vehicle. The rest is lost to the surrounding air and engine parts and to the engine's coolant. Obviously, when less combustion heat is lost, the engine is more efficient. From this picture, we can see the heat dissipation from the engine. So the radiator, the heat is lost or the energy is lost by the radiator, about 1/3 of the input. About 1/3 of the input is lost by the exhaust system, and about 1/10 of the power is lost by radiant. So the input power is 100%, but the output power is less than 100% because there is a loss due to different reasons. So output is approximately 1/4 of the input. Mechanical efficiency is a measure of how much power is available once it leaves the engine compared to the amount of power that was exerted on the pistons during the power stroke. Power loss occur because of the friction generated by the moving parts. Minimizing friction increase mechanical efficiency. So mechanical efficiency can be calculated by dividing the brake power to indicator power and multiplying it by 100%. Torque versus horsepower. Torque is a twisting or a turning force. Horsepower is the rate at which torque is produced. An engine produces different amount of torque based on the rotational speed of the crankshaft and other factors. Look at the mathematical representation of graph of the relationship between the horsepower and the torque of an engine. This graph shows that torque begins to decrease when the engine speed reaches about 1700 RPM, around here. So the torque is decreased after this point. Brake horsepower increase steadily until about 3500. After this, the brake power is increased, then it decreases or drop. The third line, this one indicates the friction horsepower needed to overcome friction or resistance created by the internal part of the engine rubbing against each other. So in the X direction we have engine RPM, and in the vertical direction we have horsepower and also a torque. So the engine speed is increased by 500 and the horsepower is increased by 20 and the torque is increased by 25. Brake horsepower. Horsepower is a term used to express the amount of horsepower measured on a dynamometer. This measurement represents the amount of horsepower an engine provides when it is held at a specific speed at full throttle. Horsepower is also expressed as FCA gross horsepower, which is the maximum amount of power an engine produces at a specified speed with some of its accessories disconnected or removed. SAE net horsepower represents the power produced by an engine at a specified speed when all of its accessories are operating. Thank you for watching this educational material. If you are interested, please share with your colleague.